All right, good day, everyone. Welcome to our YouTube lessons on carbohydrates. So, in this video, I'm going to be looking at the introduction to carbohydrates, the classification of carbohydrates, the structures of carbohydrates, and the reactions of carbohydrates. Yes, so we're going to look at all this about carbohydrates in this video. Now, quickly, we'll start with what is carbohydrates very fast. What is carbohydrates? Now, carbohydrates is a compound or a polymer that usually contain carbon, hydrogen, and oxygen in this proportion. Usually COX, H2Y, OY, or pardon me, OY. COX, H2Y, OY. Many will say, or many traditionally has defined carbohydrate as an hydrate of carbon, or would they say carbon that is hydrated. Yes, that is formula correct. Looking at the formula aspect, it is correct, but that's not what carbohydrate usually is. Now, speaking about the chemistry or more of the chemistry of carbohydrate is usually compounds that contain hydroxy, or we say they contain polyhydroxy alkanals, or we say polyhydroxy aldehydes, or they contain polyhydroxy ketones, and ketones are known as alkanones. So if you have not watched the alkanones video, check the link in the description below. You will see the link to the alkanone videos. Yes, the link to the alkanone video. So polyhydroxy alkanal or polyhydroxy alkanone can be carbohydrates, or we'll say compounds that contain carbon, hydrogen, and oxygen in this proportion, or traditionally, formula wise, many will say hydrates of carbon, or carbon that is hydrated. So all these definitions, which the most proper is these two, are the definitions of carbohydrates. Yes. What are the classes of carbohydrates very fast? Carbohydrates can be quickly classified into four aspects or four classes. So usually the first one is monosaccharides, because sugars have been seen to be carbohydrates having one sugar unit. You say you are a monosaccharide. Many say disaccharides. Yes, disaccharide, the second class, two sugar units. The next one is what we call oligosaccharide. Oligosaccharide, I'll quickly explain. And polysaccharides, the polymers, the ones we call glycans. Glycans, they are polymer. Now, monosaccharides usually have the formula of CX H2XO, or we say CN, or let's use X. Yes, COX, H. So X can be where X for monosaccharide, S can be from 3 to 7. So monosaccharide can have carbon of 3 to 7. This video will concentrate on monosaccharide. Subsequent videos will look at the chemistry of disaccharides and the chemistry of oligosaccharide and polysaccharide. Also, in another video, look at the metabolism of carbohydrates. A simple introduction on the metabolism, glucogenesis, glycolysis, the pentose phosphate pathway, and so on and so forth. So we'll look at those things in subsequent videos. Now, but quickly, in this video, I'll look at monosaccharide mainly, but let me just really define what is disaccharide. Disaccharide usually have two monosaccharide units, that's why they are disaccharides. Usually, they have two monosaccharide units, and they usually have formulas or general formula of COX, H2Y, OY. Yes, of which the most common are the ones where X is equal to 12 and Y is equal to 11. These are the most common ones. Is the most common one, X is equal to 12 and Y equals to 11. For oligosaccharides, now they have 3 to 10 monosaccharide units. So an oligosaccharide usually have 3 to 10 monosaccharide units, while polysaccharide has from 11, what's it called, 11 units of monosaccharides and above. Yes, that's what the polysaccharides are made up of. So the polysaccharides usually have the formula of 6 H10 O5 N. Yeah, this is general formula for the polysaccharides. C6H10O5. General formula for the polysaccharides. So I'm going to look at the chemistry of the monosaccharides. I'm going to look at the possible their reactions. Chemistry of monosaccharides and their reactions. So very fast, monosaccharides. Monosaccharides, as I earlier said, they contain 3 to 7 carbon. They can be classified in two ways. We can also put them further in two classes. First of all, we'll look at the functional group. We can classify them based on functional group. Yes, we can classify them based on functional group. We can also classify them based on number of carbon. So based on functional group, remember there are polyhydroxy. All carbohydrate molecule, monosaccharide molecule have hydroxy, but there's this special functional group, the alkanals and the alkanone. So a carbohydrate or a monosaccharide that have a functional group which is the alkanal or an aldehyde, that carbohydrate is known as an aldose sugar. Yes, we call that one an aldose sugar. Why a carbohydrate that have alkanone functional group, alkanal functional group is CHO. That's the functional group. Why carbohydrate that have alkanone or ketone functional group is known as a ketose sugar. So this is a C double bond O functional group. C double bond O functional group. Based on the number of carbon, carbohydrate can be triose, call them trioses. They can be tetrose. Now, what's a tetrose? 4 carbon. Triose, 3 carbon. 5 carbon are said to be pentoses. Yes, pentose, very important. Now, the 6 carbon, which are the most common, are known as the hexoses. Yeah, in the likes of glucose, fructose. Now, 7 carbon are known as heptose. Heptose, the likes of sedu, heptulose, sedu manus. So you should have 3 to 7 carbon. You are known as if you have, they usually have 3 to 7 carbon. 7 carbon as the heptulose or the heptose. Heptulose or heptose. So let's just use heptose. Heptose. So triose, tetrose, pentose, hexose, and heptose. So these are usually the classification of carbohydrates. The classification of carbohydrates. So we'll look at the simplest monosaccharides. The simplest monosaccharide. Now, the simplest monosaccharide are of 2, and they contain 3 carbon. So I call them the simplest monosaccharide. Now, the first one is the diglyceraldehyde, and the dihydroxyketone, or dihydroxypropanone. So how does diglyceraldehyde look like? This is it. Using a simple Fisher projection, it's like this with one chiral center. I'll quickly say something here. CH2OH. Now, what about dihydroxyketone? Dihydroxyketone has no chiral center. CH2OH, C double bond with the ketone functional group and the CH2OH. So this is the dihydroxyketone. These are the they are both trioses. So any compound, before I proceed, any compound that have more than one OH having an alkanal or an alkanone as a functional group is known as a sugar. Yes, more than one OH, polyhydroxy, having a ketone is also a sugar. So these ones are trioses, triose sugar having 3 carbon each. Now this one is we can call this one an aldotriose. Why do we say aldotriose? An aldose sugar and a triose sugar. I will call this one a ketone functional group. Call it a ketotriose. So ketotriose because it has a ketone functional group and it is a triose. Yes, so that's for glyceraldehyde. Now quickly, how do you get the number of chiral centers? Because I've seen some first year examination questions in some universities across the world, across the globe. Now the question goes like this. They will say, how many chiral centers are in ribose? Yes. Now the only thing you need to know to answer that question is to know what type of sugar. Is it an aldose or a ketone? So for aldoses, they have aldoses. Please take note of this. They have N minus 2 chiral centers. So if you have an aldose sugar and you know it, so just N is the number of carbon atoms. The number of carbon atom in the sugar minus 2 for aldose sugar is the number of chiral centers. Now, I said, yeah, this place is just one chiral center. If you look at the Fisher projection, which I just drew, that is the chiral center is just one. This is not a chiral center because it has two similarities. What's a chiral center? For those that don't know, a chiral center is a center with four different, or is a carbon with four different groups. So this carbon has H, OH, two different groups, CHO, which is a different group from CH to OH. So there's just one chiral center. But check, it's an aldose sugar, right? Because it has an aldehyde functional group. Now, 3 carbon, subtract 2. 3 minus 2, that is 1. It has 1 chiral center. So even without knowing the structure, assuming you just know glyceraldehyde is an aldo, is actually an aldo triose. Assuming glyceraldehyde is an aldo triose, aldoses, so N minus 2. So triose, 3 carbon minus 2. That's the number of, so there's 1 chiral center. For keto sugar, they have N minus 3 chiral centers. Yes, N minus 3 chiral centers. Dihydroxy ketone, the other hand, has no chiral center. Yes, a keto sugar, check, that's 3 carbon, 1, 2, 3. So 3 minus 3, that is 0. And if you look at the structure, looking at the Fisher projection, there is no center that is chiral. There is no carbon having 4 different groups. This carbon has 3 different groups. 2 hydrogen, this, let's say this one, so that's hydrogen, this one, OH. So if I just open it up, if I open it up, it can be opened up like this. This is how it says to OH look like. So I'm going to put H here. So these two are the same. So it's not chiral because 2 groups are the same. So for you to be chiral, these 4 groups surrounding it must be different. These 2 are different from this one, but these 2 are same. So there are no chiral centers in dihydroxy ketone. That's one way to know it. So this is the trioses. The trioses. We'll move on to the tetrose sugars. All right, still on carbohydrates. We look at tetrose sugar. Now, tetrose sugars are sugars with 4 carbon. Typical examples are erythrose and terose. Now, erythrose and terose are both aldose sugar because they have the aldehyde functional group, and they have 2 chiral centers following the N minus 2 rules we used in the first video. The N minus 2 rule says that aldose sugars have N minus 2 chiral centers, while keto sugars have N minus 3 chiral centers. So this is their structural and Fisher projection. I would really like to highlight something. Now I'll look at what we call epimers. Yeah, erythrose and terose are the first epimers we'll be looking at today. Erythrose, a 4 carbon aldose, or a 4 carbon tetroaldose, or 4 carbon aldo tetrose, the same as terose. The on the Fisher projection they look alike. Now if you watch erythrose, all the OHs are to the, or all the hydroxy group, or all the OH, pardon me, are to the right, while for terose you just watch one of the OHs to the left, that one is to the right for the 2 chiral centers. Yeah, so we'll say erythrose and terose, they differ at carbon 2. So on a Fisher projection, when H2 sugar molecule differ at a particular chiral center, such sugar molecules or such molecules is said to be such type of isomerism is said to be known as, it's said to be called epimerism. We say they are epimers. So erythrose and terose are epimers at carbon 2. They differ at a particular carbon. So one thing about epimers is that epimers are diastereomers. That means these are optically active sugar molecules. They are both D form. They are both optically active, but they are not mirror image of each other. So epimers are stereoisomers that differ at a particular carbon Yes, another example of epimers are anomers. We look at them again. So just take the Tetrose and Erythrose are epimers are carbon 2. It's another way to draw them. So you just draw everything to the right, OH to the right. You just switch carbon 2, you have Tetrose. Now there's another sugar that looks like erythrose, but this is the ketone form of erythrose, the ketone form. So it's called erythrulose. So erythrulose is drawn like this. Erythrulose is drawn like this. C. Yeah, so I have a CH2 OH, C double bond O, C OH, H, CH2OH. This is known as erythrulose. Erythrulose. Now, if you observe erythrulose, erythrulose is almost similar to erythrose, just that they are functional group isomers. What do I mean? This one has a ketone group, this one has an aldehyde group. So that's the difference between erythrose and erythrulose. So, and erythrulose is also is a 4 carbon tetrose, or 4 carbon sugar, pardon me. It has it has with one chiral center, just a chiral center, following the N minus 3 rule. So N minus 3 rule, N minus 3 chiral centers, 4 carbon minus 4 minus 3, one chiral center, which is this. So and the OH is to the right. So let me talk about this perspective form of sugar. Now looking at the perspective way, or looking at the handedness of a sugar molecule, we can see that sugar molecule can be of D and L form. How do you quickly get D and L form? Now, the highest numbered chiral center, or the penultimate carbon. And when I mean highest number, now these are the chiral centers. I already said this. Now the highest, this is carbon 1, carbon 2, carbon 3. This is the highest numbered chiral center, the highest numbered chiral center. So this guy, the OH on this guy is to the right. So say it is right-handed, D-erythrose. So this one has just one chiral center, the OH is to the right. It is D-erythrose. How which the OH was to the left? We say it is L or left-handed erythrulose. Same as this. This is the highest number chiral center, the highest numbered chiral, or we say the second farthest carbon from the functional group. 1, 2, 3, 4. This is the farthest carbon from the functional group, the second farthest carbon from the functional group. That's how you get their handedness using this perspective structure. So look at pentoses and hexoses now. Now for the pentoses, they are usually intermediates gotten from the pentose phosphate pathway in the living cell of an animal. So we'll look at that in carbohydrate metabolism. So let's look at pentoses very fast. Now pentoses are they have 5 carbon. Example is ribose. Now ribose is having OH to the right, OH to the right, or OH to one side. Now when you change the configuration or an epimer, let me use that word, an epimer, since you already know what epimerism is. An epimer of ribose at carbon 2. So changing the configuration of ribose at carbon 2, you get arabinose on Fisher's projection. Now, changing the configuration of ribose at carbon 3, we get xylose. Yes. Now, beautiful again. I quickly like to say this. These are those sugars. For xylose, if you change the configuration of xylose at carbon, now changing the configuration of xylose at carbon 2, xylose. So an epimer of xylose at carbon 2, an epimer of xylose at carbon 2 will have what we call lysose. Yes, what we call lysose. What we call lysose. So epimer of xylose at carbon 2, 1, 2, 3, 4, 5. So at carbon 2, an epimer of xylose at carbon 2 is lysose. Yeah, lysose. So very important. So these are examples of aldose sugar. You can see the way I'm drawing them using epimerism, or the streak of epimers, or the trick of epimerism to draw them. So you can quickly get their structure like that. These are the ribose of the pentose sugar. And I'll quickly like to talk about the pentose sugar somehow. And look at, these are the aldoses. The aldose part of the pentose, or we call them aldopentose or aldopentoses. Now, we look at the ketopentoses. Example is ribulose, a very great very great or great important or very important sugar in photosynthesis. Now ribolysis phosphate, which act as the enzyme, in photosynthesis in the Calvin cycle, is an enzyme in the Calvin cycle. Now ribulose is the keto isomer of ribose. So the keto isomer of ribose, so changing ribose to a ketone functional group gives you ribulose. So now here will be CCH2O. Then you put your ketone functional group there, retaining the same configuration, we have ribulose. Yes, CH2OH. So this is ribulose. So removing the H here and replacing it with phosphate gives you ribulose 6 or ribulose 5 phosphate. Pardon me. So that is ROBP or ribulose biphosphate. So 1 and 5 can replace at 1 and 5. So ribulose biphosphate. Some people call it Rubisco. The enzyme is Rubisco, ribulose biphosphate carboxylase. So all that for photosynthesis we'll look at in later videos. So for xylose again, if you or change xylose, remember xylose is an epimer. This is ribulose. Xylose is an epimer of ribose. Don't forget that at carbon 3. We said it earlier before I wiped the board. So at carbon 3, just change the configuration. At carbon 3. This thing becomes xylose. Yes, xylose. So also, if you get a keto sugar from xylose, if you get a keto sugar from xylose, if you check, now this is, let me just put, this is xylose, CHO, this is xylose, please observe, this is xylose, same thing. So now I want to replace ketone group. So I told you earlier, ketone group cannot stay at carbon 1, ketone group must stay at carbon 2. Yes, ketone group don't stay at carbon 1. Yeah, if a ketone group is at carbon 1, check our aldehyde videos. For instance, you draw an organic compound, you have ketone at carbon 1. Yeah, that compound, you have a carbonyl group at carbon 1. Let's say you have a compound like this. Yeah, it is not complete. You need an H to balance it. So obey tetravalency. What do I tetravalency in organic chemistry? In organic chemistry, each carbon must take 4 bonds. That is the rule due to excitation of the carbon electrons. So each carbon take 4 bonds. So 1, 2, 3. 4, the H making 4. So carbon 1 can never be ketone group. So ketone groups are always in carbon 2. So this compound is the ketone form of xylose, and it is known as xylulose. We call it xylulose. So xylulose. So those are typical examples of pentose sugar, and how to quickly draw them. Xylulose have how many chiral centers? Xylulose have just, now I told you the rule. It's a ketone sugar, or it's a keto sugar, N minus 3. 1, 2, 3, 4, 5. Have we? So 5 carbon minus 3, 2 chiral centers, which are steric them. Just look at the structure. You see that it has 4 different groups connected. The chiral center is a group, 4 different, or a carbon of 4 different groups. But xylose, arabinose, ribose, they are those aldopentoses. They have 5 carbon. And to get a number of chiral centers is N minus 2 for aldopentoses. So N is 5. So 5 minus 2, that's 3. So arabinose, xylose, lysose, they all have 3 chiral centers. I've seen university examination, especially first year university examination with such questions. For instance, how many chiral centers are in arabinose? 8. 1, 2, 3, 4, 5. So you see the option 1, 2, 3, 4, 5. So the answer is going to be 3. Arabinose, xylose, they have 3 chiral centers. So without wasting much time, we'll quickly move to the hexose and the heptose sugars. Now, for the hexose sugars, which are the most common monosaccharides, Now, I have before me allose. Now, from allose, I can draw, or I can get the Fisher projection for about 6 or 7 hexose sugar. Now, just with the concept of epimerism. So, for allose at carbon 2, an epimer of allose at carbon 2 is Altrose. So, just change the configuration at carbon 2. We have Altrose. So epimer of allose at carbon 2 is Altrose. Altrose. So we have Altrose. Just so you see what carbon 2 differ. So I have Altrose 1, 2, 3, 4, 5, and 6. This is, I think it's 6. 1, 2, 3, 4, 5, 6. So this is Altrose. Now, an epimer of allose at carbon 3 is glucose. Epimer of allose at carbon 3 is glucose. So epimer of allose at carbon 3 is glucose. Epimer of allose at carbon 3 is glucose. Epimer of allose at carbon 3 is glucose. So this is glucose, which is the most popular sugar. Glucose is blood sugar, very popular blood sugar, and it's found in grape and many soft drinks. Now, this is glucose. So now, and from glucose, you can draw many others. So you see Altrose, you see allose, you see Altrose. So I've gotten allose, Altrose, glucose. So I can draw like three other. Now, for instance, let me show you how to draw. Mannose and galactose from glucose. Now you see, you get that an epimer of glucose at carbon 2 is mannose. So if I have glucose and at carbon 2, I have glucose at carbon 2, I change the orientation. So I get at carbon 2, instead of having the OH to the right, that's to the left, and C, then OH here. So this become mannose. So an epimer of glucose at carbon 2 is mannose. So we have mannose. So I'd like you to guess or help me draw, if you are there with me, help me draw galactose. Galactose is an epimer of glucose at carbon 4. Pardon, this at carbon 2, that's where mannose is the epimer. Galactose is an epimer of glucose at carbon 4. So try and draw galactose. So an epimer of glucose at carbon 4 is galactose. So try and draw galactose before I put it down. I'm about to put galactose down. Try it. I'm waiting. Try it. Try it. All right, the structure of galactose will be CHO, OH, H. So just the same as glucose. But at carbon 4, orientation is going to change. So the difference between galactose and glucose will be at carbon 4. Please watch it at carbon 4. So CH2, OH. So galactose alongside glucose is found in lactose, which is milk sugar. So lactose is a disaccharide. We'll look at it later. Lactose is a disaccharide which is made up of galactose and glucose. So galactose is a monosaccharide found in milk. Also, from galactose, I can get what you call talose. Now, talose is an epimer of galactose at carbon 2. So I have talose. So talose is an epimer of galactose, at carbon 2. So at carbon 2, if I should change the orientation, so CHO at carbon 2, if I should change the orientation, of galactose at carbon 2, I got talose. So at carbon 2, you see, you get CHO, C. So we have now H, OH. Now you observe, I changed carbon 2. So we're gonna have C. So this is Taurose. Now if you observe, the difference between Taurose and galactose is carbon 2. Carbon 2. You see at carbon 2, you have Taurose there. Taurose at carbon 2. We have Taurose there. So at carbon 2, Taurose is so the difference is carbon 2. So you watch the difference between galactose and Taurose. It's not carbon 2. So that's that. That's one way to draw them. Now quickly we look at the heptoses. Heptoses. Remember I said monosaccharides are sugar that they have 3 to 7 carbon atoms. 3 to 7 carbon atoms. So it's not 3 to 6. So heptoses such as pseudo heptulose and pseudo mannose. Those are the two common examples. So examples of heptose, example of heptoses are the monoheptose and the pseudoheptulose. Now the pseudoheptulose, the heptulose are usually the ketone form is in the ketone form. So the monoheptose is in the formaldehyde. Also, I can also change this one, this monoheptose. So it's like mannose, adding an extra carbon to mannose. So adding an extra carbon to mannose in the D form. So if it's L form, there's to be L. Man, remember how many chiral center does it have? This is an aldose sugar. So 7 minus 2 for n minus 2 for aldose chiral center. Aldose white ketose is n minus 3. So I have 7 minus 2, that's 5 chiral centers. So this is the highest number chiral center. So the highest number chiral center, and the OH is to the right, so it is in the D form. Quickly, for monoheptose, I can also convert it to the functional group isomer, which is a ketone form. So I can just quickly change it. How do I change it? So here will be CH2OH, CH2OH, and I have a ketone group here. So it's no longer monoheptose, it's now monoheptulose. Monoheptulose. So this is monoheptulose and a ketoheptose sugar. Ketoheptose sugar. So this is how we draw them. Now quickly, and I'll quickly say this, so you try it by yourself. When you get glucose, the ketone form of glucose is known as fructose. So the keto form of glucose is known as fructose. So we say glucose and fructose are functional group isomer, one have aldehyde, the same orientation, just that one is in the ketone form, one is in the aldose form. Glucose is an aldose sugar, fructose is a keto sugar. So they are both hexoses, just that glucose is aldohexose, while fructose is ketohexose. So those are the structures basically for monosaccharides, for the common monosaccharides, the structures for common monosaccharides. We'll quickly look at the look at the reactions of monosaccharides very fast. About 6 reactions I have to show you. But before I look at the reactions, now let me quickly talk about what is known as mutarotation. Mutarotation. So let's quickly look at what is known as mutarotation. 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 So mutarotation. So mutarotation is like an epimerization reaction. So I'm going to use glucose for instance. So the structures of carbohydrates we'll be showing since are the Fischer projection. Now, looking at the Howard projection and how it is drawn, the cyclic structure, Howard observed sugars in solution. I have said that in solution, Howard, his name is Howard. So Howard projection quickly. Howard projection. Howard projection. So he observed sugars in solution and said, it's an English biologist, and observed something about sugars. Let me use glucose for instance. Glucose, allose, always to the right, but an epimer of allose at carbon 3 is glucose. Yes. So glucose, this is glucose. 1, 2, 3, 4, 5, and 6. So this is glucose, glucose, glucose. So glucose. Now for glucose, according to the Howard projection, According to our words, in solution, aldehydes and OH normally react, especially the aldehydes that is showing the chirality of the sugar molecule. So this OH usually attacks this aldehyde. And in chemistry, if you watch our videos on alkanals and alkanols, when aldehydes react with ketones, when aldehydes react with alcohol group, aldehyde plus alcohol group, we form what they call acetal or hemiacetal. I'll quickly just drop that. I'll say aldehyde or an alkanal plus an alcohol group, you get an hemiacetal. But if alkanals or aldehyde react with two molecules of alcohol or two OH molecule, two OH, we get an acetal. So one is hemiacetal, one is acetal. So our form of glucose is the hemiacetal form. So what I'll tell you, this OH is in this manner, is more like an addition reaction. So what happens is this. This is what happens. Now, this center is electron rich, hence it is nucleophilic. So what happens is that this OH releases H, and that H attacks this center. So that H attacks this O, so the H comes here. So please just watch, watch. Comes there like that. And this, remember the H left. So basically, if I should show you, so that's a double bond. So this place is nucleophilic. Yes, and it's an electrophile, so it's electron rich, but it's a nucleophile, it's electron rich, so it loves a positive center. So this center is nucleophilic. So aldehydes and ketones are what we call nucleophilic addition. So this O takes negative and this H is positive. So what happens is that the H attacks the OH, if you know your electromeric effect. So electromeric effect tells me that here forms a partial negative, here forms partial positive. So it attacks it and we get OH here. If you're watching it, OH comes there. Then the O attacks the carbon. So the O attacks, because the carbon is positive, the O attacks the carbon. So at the end of the day, we're going to have a structure like this. We're going to have a structure like this. If you watch very well, we're going to have a structure like this, which is like this. I have OH, then I have O. Remember, there was an O there. That O, the O is here. This is the O. This is the O. There was no O there, so this was just the O negative. The O negative attacks the positive carbon. You know, this O was also negative here, so it attacks the positive carbon. So as it attacks the positive carbon, so it forms something like this. Yes. So for many textbooks, they try to bring out the O and place it at the middle like this. Try to bring out the O and place it at the middle like this, such that we have something like this. So this is an hemiacetal form of a carbohydrate. Many call it the pyranose structure. So I can use to get the pyranose structure of carbohydrates. So I'll show you how it looks like now. All right, I'll go over the hemiacetal formation again. Now, remember, if it's a ketone, if this sugar was a ketone sugar, you form an hemiketal. Just take note, one aldehyde group plus one OH group and one alcohol group gives me an hemiacetal. One ketone group plus one alcohol group gives me an hemiacetal. I'll go over this again. Now, this was glucose. So let me show you this formation. This was glucose. The CHO group is like that. I said earlier that this center is nucleophilic. So this center, though because of the double bond, when we say it is unsaturated, but this compound does not have a carbon to carbon double bond, so it's not an unsaturated organic compound. But this C2O is unsaturated, that means can undergo addition reaction. So but the type of addition it undergo is nucleophilic addition because it is electron rich. Now, how will that happen for acetal or hemiacetal formation? Now, I told you for electromeric effect, here tend to take a partial negative charge, here tend to take a partial positive charge, the elimination of one of the double bonds. which I will not show. Now, this place, now during that reaction, because OH can be divided into negative and positive, so this O attacks the carbon, this O here attacks the H. Coming over that again. So what do we now have as our new structure? During addition reaction, a bond is broken. So the bond is broken. Here is OH. Now, this carbon forms a bond. So it now make the compound more like cyclic. Forms a bond with this guy. Yes. Compound will now be cyclic because the carbon will have to bend to go and form that bond. So it will not be cyclic. Yes. This is what I am talking about. And I said some textbook will take the O to the middle of the compound and put it here like that. This is the hemiacetal form of glucose. Is the hemiacetal form of glucose. So drawing this thing in a cyclic manner, I will observe that I will have a kind of a 6-member organic compound. That I'll have something like this. I'm going to have something like this. This is the O. This is the O. This was the carbon having the functional group before. This is carbon 1. So this is carbon 1 now. So let me number the carbon for easy recognition. Carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. So that is 1. So 1 is bonded to 2 bar. Yes. So 2 is bonded to what? 3. Yes. 3 is bonded to 4. Yes, this is 4. 4 then is bonded to 5. So this is 5. Then carbon 5 have a CH2OH, which is 6. This carbon is 6. So like that, this compound, this cyclic structure I just drew, it resembles an organic compound that is cyclic, that is 6-member. An organic compound that is 6-member. Yes, it resembles this organic compound. And this organic compound is usually known as pyrene. What do we call this organic compound? Pyrene. So when sugar is in the award or 6-member form, we'll say that sugar is in the pyranose form. So if you're looking at the nomenclature in another biochemistry video, I will call this 6-member glucose glucopyranose. So let me put my OH and my H. So at carbon 1, I had a OH here, up, OH there, up. Carbon 2 also had OH down, H up. So down is 2. So at carbon 3, the OH was now opposite the way the OH is on carbon 2. At carbon 4, I have the OH also to the right. So let's assume the right is down. So then this carbon carrying the CH2O is just have only H. So it has just H. So to the left. Let's just put the H there. Just H. So I quickly have to make some comment. Now I said this carbohydrate, this glucose, is now known as the pyranose form. And is in the hemiacetal form. So many call this guy. We call this guy glucopyranose. So this can be glucopyranose. But the names or the IUPAC name are not my priority in this video. My priority in this video is this carbon. So the carbon carrying the functional group in the original structure, if I should revert this glucose, I should have something like this. Now, reverting this glucose make me have something like this. I have double bond OH. So yeah, so remember the attack came from these two. The attack was between 1 and 5. Why did it happen between 1 and 5? 5 is the highest number chiral center. This one determines the handedness of the carbon. So 1 is the functional group. So aldehyde and alcohol group, they attacked each other. Now, so it occurs between 1 and 5. The carbon initially carried the functional group before. If you watch what we did earlier, it here turns to OH. So this carbon carrying functional group turns to OH. Yes, the OH comes there for this other O to attack this carbon. So, but this carbon carrying the functional group before is carbon 1, and that carbon 1 is known as the anomeric carbon. So on the remember this projection, this cyclic form of joint sugar is known as the Howard projection. It was first observed by Howard. So this Howard projection this outward projection, the carbon 1 is known as the anomeric carbon. Yes, anomeric carbon. So when two sugars differ in the anomeric carbon, those two sugars are said to be anomers. Let me show you something. Now this is glucose. Now because the OH is downwards because on the anomeric carbon the OH is downwards, we'll say that this is an alpha glucose. We say this is an alpha glucose because the OH is downwards. If the OH goes, or the orientation of the OH changes and it goes upwards and the H comes down, this glucose becomes beta glucose. This glucose becomes beta glucose. So that glucose becomes beta. So for alpha, on the anomeric carbon, the OH is down. For beta, on the anomeric carbon, the OH is up. So those two compounds, or the alpha and beta glucose, they are known as anomers. So alpha glucose and beta glucose are known as anomers, and they are type of epimers. What are they type of epimers? Alpha and beta glucose will differ in orientation at a particular carbon, like the way epimers do in the Fisher projections. So we look at Mutarotation